Hello, my name is Krill. Some of you might know me as a Discord user Buzz, and welcome to my presentation about why I think deferred shading is always a bad idea and you should never use it. The intended audience is experienced graphics programmers, and in general you are expected to know about all relevant terms and technologies, although I will be leaving links to detailed explanation for all presented ideas and concepts, and will be trying to give a nutshell high-level overview, so hopefully it's going to be useful for beginners as well. So let us start. We're going to start with the overview of what we are going to talk about. First, there's some common things that are shared between both types of the renderers and are relevant to how these renderers perform. We are going to talk about mesh clusters, how to generate them, how to render them without mesh shaders, which is important. We're going to use regular instancing and how to do frustum and backface culling for them efficiently. The next topic is the GPU scene management. We are going to talk without going into details about coarse object culling and GPU occlusion culling using the depth pyramid method. After that, we're going to deep dive into optimized, deferred, and forward renderers, what data they store and process, how lights and shadow works, how decal works, and how all this impacts the post-processing. Finally, we're going to compare them and make some conclusions that will hopefully make you change your mind about deferred shading. Content warning. This presentation contains subjective strong opinions. Those will be clearly marked with purple color and a distinct audio cue. You are free to disagree with them if you wish, and you don't have to fight for it if you do. So, let us begin. What is a cluster and how do we get them? Cluster is a small portion of the mesh that generally contains up to 126 triangles. They are grouped together in a way that satisfies a few conditions. First condition is triangles that are spatially close together will be in the same cluster. And second condition is minimizing the size of the bounding cone. I would highly recommend to use the mesh optimizer library for this. It essentially has two functions: meshopt build _build meshlets and meshopt _ compute meshlet bounds that will do all the heavy lifting for you. And on the right side you can see the visualization of how a Stanford bounty was clustered with the mesh optimizer. Each cluster has a bounding box and a unit bounding cone computed for it. We're going to use the bounding box for the regular frustum culling because it's trivial, and we're going to use the bounding cone to do an additional backface culling and remove all clusters where all triangles are facing away from the camera. You only need one dot product to do that. It's practically free, and you can see a code example that does just that. So how do we render these clusters? Contrary to the popular belief, you don't need mesh shaders to do that. Yes, mesh shaders are more efficient. If you really want to, you can transparently enable them when supported, but you don't have to. Strong opinion warning: I don't think it's worth implementing a mesh shader code path for RTX GPUs. It's just not worth the effort, but feel free to do so if you want, as long as you're still targeting the older hardware. So how it looks in the pseudocode. Here's an example. We have the draw indexed indirect command, which is basically a built-in struct. For each source cluster, we have a bounding cone and a draw command that is used to draw it. All cluster data is stored in one buffer. The draw commands contains correct offsets into that buffer. Here's how the culling shader might look like. We're going to omit frustum culling, but you get the idea. Reset the draw counter in the first compute shader invocation, then fetch the input cluster, do the cone apex test and the frustum culling. If both have passed, then atomically append it to the global buffer. In the real world, you will also want to store a cluster transform somehow, for instance an index of the corresponding object that it could fetch the transform data from. Again, I'm omitting this part to better demonstrate the idea of cluster culling. Now let's discuss the GPU scene management, or rather let's not discuss it. It's not relevant to the comparisons that we're making. The GPU scene management has to be there, but it is irrelevant how it is implemented. You can Google some approaches. There's BVH, there's scene graphs on the GPU, you can run an ECS on the GPU, etc. It is irrelevant. Clusters, on the other hand, are relevant, and I'm going to show you why when we get to the forward renderer section. When it comes to the GPU scene management, what we care about is the following. It has to have a concept of an object that users can place in the world. The objects can have multiple meshes and a separate bounding box. They are organized in a hierarchy. You can look up flex queries on how to do it efficiently if you want. We also assume that streaming is handled as well, so everything that gets to the GPU is actually loaded and ready to use. And I would refer you to a wiki guide which has an excellent article about it. It's called GPU driven rendering. I would highly recommend that you read it at some point. First things first, no CPU culling. Do not process clusters on the CPU, do not do anything with them on the CPU, and don't do any culling at all on the CPU. What we should be doing is we pre-record all our command buffers offline, ideally during a loading screen, and these command buffers should contain everything that's loaded, whenever it's visible or not. And then we submit everything to the GPU and let the GPU do the work. Of course, in the real world, we'll need to re-record them occasionally if something has changed, and in this case, we also assume that this is handled and we don't have to worry about it because this is not the topic of this presentation. I regret to inform you that we won't go into depth about depth pyramid culling either. We just assume that you have it and it works. The general idea is that you have some sort of extremely low poly occluder meshes that you render into a low resolution depth buffer first. These meshes can be generated with a mesh optimizer if you want to, but there are better silhouette-based approaches that would yield less triangles with the same results. Then you generate MIP maps for the depth buffer, but you're not going to use a regular MIP map filtering, you're going to use a min or max filter. That depends on whenever you're using a reverse depth, which you should always use, by the way, and it's not an opinion, it's a fact. The depth buffer with such MIP maps is called the depth pyramid. So then we have a compute shader that takes the bounding box for each cluster and tries to progressively test the corners of this bounding box against the MIP levels of the depth buffer, starting from the lowest MIP level and going up when needed. If this test is passed, we then append the draw arguments to the global draw argument buffer, similar to how Apex culling worked. Again, Wiki Guide has an excellent article and I highly recommend reading it. So here's the high-level overview of the GPU scene management. We start with all objects. First, we assume that streaming is already run at this point, so all the objects that we have here are valid and loaded. We run a coarse culling pass internally, which produces a buffer with our input cluster data and the culled objects. These objects then go into the frustum and apex culling passes that generate a filtered draw indirect buffer with a small subset of clusters that are actually visible. At the same time, we use the coarse culled object data to draw visible occluder meshes into the low resolution depth buffer and generate a depth pyramid. We then take backface culled clusters from the frustum and apex culling pass and feed those into the cluster occlusion culling pass. They will be tested against the depth pyramid and a final draw argument buffer will be generated. And that buffer in turn goes into the renderer, be it forward or deferred. Also note that in the real world, all the culling passes would actually be one single pass for performance reasons, but I've separated them in this overview to better illustrate the idea behind it, and you'll be seeing this a lot. Finally, we got to talk about deferred shading. First of all, I assume that you know what it is and how it works. So we're going straight into what I would consider an optimized deferred shading render. We'll start with packing the data. You want to pack as much as possible to reduce memory bandwidth, which is the #1 performance bottleneck nowadays. So what I suggest here is 160 bits per pixel G-buffer layout that also has a free 24 bits for various game-specific data. If you don't need that, you can shrink it a little bit further, but for this particular use case, we would need two render targets. One is RGB32 uint, and the second one is RG32 uint. The data that we need for the render is the following. We need an albedo color, normal, emissive, roughness, metalness, and TAE motion vectors. The first three are pretty straightforward. Albedo, normal, and emissive all go directly to the first texture. Albedo is packed into the first 24 bits of the R channel, and we have an 8-bit spare data there for game-specific stuff. Normal is packed as RGB 11, 10, 11, which means that it's a 32 bits where each channel has either 10 or 11 bits. Another strong opinion warning, it could also be packed as RGBE shared exponent 9995. I think that will yield quite a bit more quality there. We pack it into the G channel of the first texture, and emissive is packed as an RGBE shared exponent 9995 into the B channel of the first texture. Roughness, metalness, and TIA motion vectors are packed into another texture. It's handy because there is things like screen space reflections and some part of TIA that only need the motion vectors and roughness. So we can save some memory bandwidth and avoid sampling the main texture there, and this gives us a little bit more performance. So this is going to be an RG32 unit texture, as I said. We first pack the 15 bits of roughness and 1 bit of metalness into the first 16 bits of the art channel of the second texture. Roughness is generally needs 16 bits of precision anyway, but 15 bits could do okay with some quality loss, and probably nobody will notice. Metalness is usually 1 bit binary data. We then pack two 16-bit floats into the remaining channels to store the motion vectors. And then there is also 16 spare bits left for game-specific data again. If you don't need that, then feel free to pack full 16-bit roughness and 16-bit metalness instead. It will have a bit higher quality. In general, with this approach, you get 24 bits of game-specific data in total. And in general, based on my experience, you would really need that for the game. So this is there. Let's talk about the lights. For rendering the lights, you pretty much need to do a tile-based or cluster deferred renderer. Another strong opinion warning: seriously, please don't draw spheres or cubes that fetch the G-buffer and calculate the lighting. You lose so much bandwidth when your lights overlap that it's not even funny. It's 2023 anyway. We won't go into much details about it works, sorry about that. I'll just refer you to the practical clustered shading presentation by Homos, also known as Emil Persson, and this is the nutshell what he's doing at Avalanche. They have a camera-aligned 3D texture where each texel corresponds to some area in the world, and each texel stores information about the lights that it contains. The shader then fetches the cluster based on the view space coords, and this cluster, then using this cluster, it fetches the lights that are touching this cluster and loops over them and calculates the lighting. We also assume that this part is optimized and scalarized, but it is really the same for both deferred and forward, so we won't go into much detail about scalarization here. Important thing is you can do this binning both on the CPU and the GPU, but the GPU is much more preferable for performance reasons because you won't be able to do a lot of lights if you're feeling that data structure on the CPU, and you won't be able to have the same level of granularity because smaller bins are way better because you will loop a lot less lights per tile that way. Let's talk about decals. First of all, I assume that you know what a decal is. It is a texture or a set of textures projected on top of geometry. First of all, let us really try to avoid adding an additional render target for decal blending. This approach is typically called the debuffer, and my suggestion is to go with cluster decals instead. Bit of a background: debuffer works by adding another RGB render target and rendering decals as cubes into that. The decal shader then projects the actual decal data on the geometry using the depth buffer. And then this debuffer is composited on top of the regular G-buffer before the main shading pass. Again, we won't go into much detail about this. I would again refer you to the excellent Rendering the Hellscape of Doom Eternal presentation that covers this topic in excessive detail. Here is the nutshell overview. The key idea is actually exactly the same as with the clustered lights. We have a camera aligned 3D texture and we bin decals in the exact same way as we bin the lights. In this approach, each decal will need to store position, rotation, quaternion, scale, texture, or a decal material ID and some sort of decal flags. And then the shader fetches the cluster based on the view space coordinate and loops over applicable decals and projects them to the object. What are the key benefits? First of all, performance. These are much faster than debuffer decals for the same reason why clustered lights are faster. You save a ton of bandwidth, and bandwidth is the #1 performance bottleneck today. Second is flexibility. Cluster decals are resolved in the main shader before the shading pass and before the G-buffer is written. This allows us to do things that are not possible with debuffer decals at all. For example, parallax decals. They will need to modify the UV before you sample material textures. Alpha cutout decals, you can do alpha cutout and make holes in the objects, although be careful with discard because it disables high Z feature and has a huge unintuitive performance impact. You can also change material properties and motion vectors in place for free without a separate composition pass. You just resolve. You can also resolve some of the decals in the vertex shader and apply vertex displacement, etc., etc., etc. And of course, they can do everything that deferred decals can do. So there's no reasons not to use them. So now let's talk how it all ties into post-processing. Post-processing itself is actually exactly the same in both deferred and forward, and we'll talk about why it is like that later. However, before post-processing, you need to run your shading pass to calculate the lighting. It takes the G-buffer as an input and produces a lit HDR texture output, which is RGB 111011 or RGB shared exponent 9995, depending on like what you like. This is then fed into TIA and the post-processing. You render opaque objects first in the G-buffer, then run the shading pass. And another strong opinion warning: after you run the TIA and the shading pass results and produce the NTLS shaded results, you do not want to run TIA on translucent objects. If you do that, then your image quality will be absolutely grotesque because you cannot have correct motion vectors for translucent objects. Again, this is a strong opinion, so you are free to disagree with me here, but as a player, I hate it. After you render translucent objects on top of, you render translucent objects on top of the NTLS texture. And this is actually an oh shit moment, because you cannot render translucent objects with deferred shading. You actually need to have a forward render in place to correctly render and light those. Which is funny, but once that is done, you basically feed the results into your post-processing passes. Here is another high-level overview of the rendering process. So we start with the G-buffer on the left that includes frustum and occlusion culling. Then this feeds into the shading pass, then TIA, then translucence with forward shading. After that, we run our regular post-processing. So I have two big examples here. This is screen space reflections and depth of field. For screen space reflections, you need to take a lot of samples of G-buffer B, and you need one sample of the shaded color from the TIA pass. So we do the ray marching using roughness and depth. Then once the ray march is done, we sample the TIA to get the final color. Then this feeds into the depth of field, tone mapping, and other post-processing that is hopefully all merged together in a single pass. Oh, and it's going to need one normal sample from G-buffer A through to construct the initial ray. You might even want to pack this to G-buffer B, but I'm too deep into making this presentation to change that. I'm sorry about that. If you want to do the motion blur, it has the same idea as the SSR, but you also need to take many samples from TIA output to accumulate the color along the motion vector. Once this is all done, we do the tone mapping and final post-processing, and then output the results to the screen or the window. Let's talk about performance concerns with deferred shading. So the main concern, as I mentioned it a couple of times already, is bandwidth. It's the number one performance bottleneck, and you cannot really shrink the G-buffer further than 160 bits per pixel. This means that your G-buffer pass will be expensive, and there's no way around it. Another big concern that is often overlooked is that when you use compute shaders for your shading pass, you actually make your post-processing slower, and I'll show you how. This happens due to render target compression that all GPUs and all vendors implement in one way or another. AMD calls this DCC or delta color compression. NVIDIA and Intel have very similar technologies supported. So what this does is all render targets are essentially compressed right on the GPU on the fly to save the bandwidth. This compression happens during regular render passes, so your pixel shader outputs are compressed on the fly and written into compressed storage. And this is how the GPU sends the bandwidth there. However, writing to a render target from a compute shader, or in general in any other way except for the copy engine and rendering passes, is going to disable this compression. So how it works is you'll get a non-free, it's not expensive, but it is a non-free decompression when you do layout transition to a writable UAV And this render target will stay decompressed forever until you clear it and do a layout transition into color attachment state on the next frame. Sadly, there is no way around it. You have your compute shading pass, your TIA and SSR are going to be up to 10% more expensive for no obvious reasons. And this is sad. Finally, let's talk about the forward renderer. Again, I make this big assumption that you know what forward shading is and how it works. So first of all, it might be counterintuitive, but forward shading still produces a G-buffer, but a much smaller one and in a different way. The main difference with deferred shading is that forward renderers calculate the shading in place during the main opaque pass. This pass has some mandatory and some optional data. Mandatory data is an HDI shaded color, which is packed into 32 bits, has format RGB 111011. As much as I love the shared exponent format, we sadly cannot use it here because it doesn't support alpha blending. The GPUs cannot render natively to RGB shared exponent formats, and you have to pack it manually in the end of your shader. And TIA motion vectors that are 2 vectors packed into a 32 bits, exactly the same as with deferred. And now you have an optional data. So if you have SSR enabled, screen space reflections, you need to output normals and roughness. And you generally need 2 channels for that, but the packing is the same as with deferred shading. You pack RGB 111011 or RGB shared exponent 99995 into the blue channel of the texture, and roughness and metalness, and roughness with metalness into the remaining 8 alpha channel. Now this is an important part. If you don't have screen space reflections enabled, for example, you're running a low graphics preset, or you're running on a previous generation console, then you can effectively scale this entire thing down to 64 bits per pixel compared to the 160 bits per pixel that we had with deferred shading, which is a huge optimization. And you cannot do this with deferred shading at all because you need the normal and roughness for the shading pass. The scaling down part is actually of paramount importance. The Switch is a huge market, the PC is a huge market. PC accounts for almost 30% of all sales. As of time of this recording, end of the year 2023, the Steam hardware service says that approximately 20% of the PC market is GTX 10 series GPU, and a few people even use AMD and Intel cards. Jokes aside, Intel is actually growing really well and soon will be an important budget card with a significant market share. So to put it simple, if your game does not run well on those GPUs with a low graphics preset, you're going to lose a lot of money and customers. So what are the key benefits of the forward renderer? First of all, we reuse and share a lot of code from our deferred renderer. We reuse mesh clustering stuff, we reuse occlusion culling, and post-processing, and all this stuff is exactly the same. The first actual benefit is that translucent objects are naturally supported in the forward renderer, and they do not require a separate code path like in deferred. Forward renderer is inherently more flexible, so you want some weird lighting models for cloth or anisotropic metals, go for it. There's no limitations or additional overhead. If you wanted to do this in deferred shading, you would need to store that material flag in the G-buffer and branch on it. Not to mention that you only have 24 bits of game-specific data there that you probably want to use for other purposes as well. You get much more options for scaling down. Apart from disabling SSR and cutting down the G-buffer in half, some objects can use less textures, others can do more approximated math to scale down the quality and get more performance that way. Again, you don't have a good way of doing it with the deferred shading because you'll have to branch on those, and branching is not free. There are also an additional savings in the form of not having a shader pass, so you don't need that extra texture at all and don't need an extra pass to fill it. So this is again less bandwidth and less memory usage, and also specifically on Xbox this also means that your ESRAM management will get a lot easier. So this is the overview of the forward renderer. We have our forward G-buffer pass that feeds directly into TA. Then we have exactly the same post-processing stuff with optional screen space reflections and depth of field. It's not that much different. Most of it is the same. So now the performance concerns and caveats. First of all, you need a depth prepass, otherwise overdraw will destroy your hopes and dreams. If you're going to complain that it's expensive on the CPU, no, it's not. Remember, we are not doing anything on the CPU because we pre-record our command buffers, and the GPU is doing all the scene management work. Another common complaint, it's expensive on the GPU. Again, no, it's not. Depth only pass is a fraction of the cost if no pixel shader is used, so all fully opaque objects that don't have an alpha cutout are going to be really, really fast because the hardware has a special code path to handle it. On top of that, you can also use a two-path depth pyramid culling to help you. So what you'll do is basically you run the initial depth pyramid with low poly occluders, as we've discussed earlier. Then you run the depth prepass with occlusion culling results. After that, you generate a depth pyramid from your regular depth prepass depth buffer, and then you run another depth pyramid occlusion culling and test against the other depth pyramid, which will effectively remove all clusters that are occluded by the rest of the scene, and you'll save a lot of vertex processing. But keep in mind that this might not work that well if you don't have a lot of stuff to occlude. Last but not least, let's talk about the number one issue with the forward renderers, triangle overshading. Not going into a lot of details here. It happens because GPU don't shade individual pixels. They do it in 2x2 groups called quads. So when triangle overlaps a pixel center, the GPU has to shade the entire quad even if it only needs that one pixel. And this particular example, you can see the GPU is running a pixel shader 12 times but only writing 3 pixels. Fabian Gizen goes into great details of why this works the way it works, so I'll just refer to you to his blog for more information. For now, we just accept that this is the way things work. So what do we do with triangle overshading? Nothing. I mean, apart from kidding, in general, this is solved by making good level of detail meshes and watching the triangle density. This is not an exclusive issue for the forward renderer. Deferred rendering suffers from it as well, but to a lesser extent. So you still have to watch the triangle density in a deferred renderer. However, I hereby claim that the bandwidth savings in the forward renderer more than make up for this difference. Another strong opinion warning, probably the strongest opinion in this entire presentation. You actually should know upfront what kind of art direction your game is going for, and your job is to support it. If you don't need nanite style pixel sized triangles, and another strong opinion, I think this is a really bad business choice for multiple reasons. Key reasons being art production, hardware support and sales, then forward renderer will do just fine. If you actually need that kind of art direction, then this is an entirely wrong presentation for you because neither forward nor deferred are suitable choices here. You actually want to use a triangle visibility buffer renderer with compute shader software rasterization, but that's a whole different topic that would take hours to discuss. The most important thing in this discussion is you need to make sure your games run on enough GPUs and makes enough money to keep the lights on, and this will be exceedingly hard if you go for that kind of art direction. So just a reminder, your job as a graphics programmer is to support the chosen art direction for your game, and you need to select the right trade-offs to ship the game. Let's finally go directly to our conclusion and comparisons. Starting with the pros and cons. Forward shading, 128 bits per pixel G-buffer, less expensive by default. Deferred shading, 160 bits per pixel G-buffer plus 32 bits intermediate shading render target. Forward shading scales down to 64 bits per pixel, and again, scaling down is important. Deferred shading doesn't scale down, always 160 bits per pixel main pass plus the 30 bit per pixel shading render target. Forward shading, you have more flexibility with materials and shaders. Deferred shading, you have less flexibility with material and shaders because it's decoupled. Forward shading, you do not need a separate code path to support translucent geometry, it just works. Deferred shading, you actually need a full separate forward path to translucent geometry, which is a lot of maintenance cost. And now, the con of a forward shading is that it suffers a bit more from triangle overshading, although I don't think that it's that big of an issue, and the benefits far outweighed the negatives here. And deferred shading suffers a bit less from triangle overshading, which is probably the only pro that I can find. So, finally, the question is deferred shading really worth it? I think not. That's all I had for today. Thank you for your attention. Here's the list of all references that I used throughout the presentation. Please like and subscribe so that I can quit my job to become a YouTuber, and I hope you have a wonderful day.